So let's get started. So today what we're going to be doing, this is, as a heads up, today's the kind of like the last day of structural technique-based stuff, I guess is sort of how I'm thinking about. We're really going to pivot into methods, kind of direct methods going forward. The bifurcation is a little artificial, but I think going forward, what we're going to be doing is really talking about techniques that people use in different papers to kind of generate identification. We've been really just acting as if we have an experiment or something that was randomly assigned. And probably for half of you, you were saying, okay, well, that's great, but I don't necessarily have an experiment. Kind of what are the ways that I'm going to generate that kind of design? And so hopefully today, what you're going to get is the ability to do a little bit more on technique, and then starting on Thursday, we'll move into difference and difference. So today what we're going to be going over is hierarchical Bayesian models, and I'm more generally talking about Bayesian shrinkage estimation. So the way that we're going to do this is what we're going to be talking about is like, we've really already kind of touched on the idea of shrinkage, right? So when we talked about lasso and regression, I kind of mentioned it, that there's a whole bunch of other types of regularization and shrinkage estimators one can think about. So we really focused on lasso for reasons related to this model selection point. But more generally, this idea of shrinkage kind of sits in this context, actually, that hierarchical modeling and Bayesian analysis really makes very concrete. We're going to kind of give a way of thinking about those contexts in a broader setting. And what we're going to be doing is studying a framework for thinking about two basically simultaneous features of estimates that we typically have. There's kind of two things that are typically going on when we estimate things. When we see, for example, different estimates or variation in estimates across things, is we typically have two things going on. One is that we have estimation uncertainty, right? So much of the time when we've been doing traditional frequentist analysis and the stuff we've been doing so far, the idea has been, well, we have some estimate that we get from an estimator, and then we talk about its asymptotic distribution. We talk about ways of talking about inference on how basically intuitively what everybody has in mind, although it's not the formal way to say this in a frequentist sense, is to say, look, I want to know kind of how close this is to the truth, right? It's like, so the true frequentist definition for confidence intervals, I always sort of get wrong, but the idea is to say, let's get another sample of the data. How close would we be to the true value of that estimate? What we're going to be getting into today is kind of the Bayesian way of talking about this, which is to say, like, look, there's an underlying probability distribution for our parameter of interest. It's actually, there's a distribution for it. And we can talk about uncertainty in that distribution. Maybe if we have more and more data, we kind of more and more tightly be able to know where the true parameter is. And that's what we're going to be trying to accommodate. That's one feature that goes on, right? Is this idea of estimation uncertainty. We just have noise in our ability to estimate things. And that's always the case. And then the second thing, though, that exists that's kind of more real, and that is the sort of thing sometimes we really care about, is true heterogeneity. Sometimes you think about, maybe the simplest version of this is to think about, we have different means in what happens, right? So maybe we all went and we all threw a ball as far as we could. So like all of us in this class, we could all measure ourselves doing some sort of activity, throwing a ball as far as we can. We could do it many, many times to try and estimate it. We might have noise in the way that we estimate something, but then there's also potentially true heterogeneity amongst ourselves as well. And so the tension there that's always sort of baked in when we think about testing for differences between things, testing for different parameters and thinking about heterogeneity is that, well, we have two conflicting features going on. We have estimation uncertainty, we have true heterogeneity, and how do we kind of separate out the two? And what the modeling is, the goal today when we're thinking about multiple estimates or things across different estimates, or just more generally thinking about these parameters, we want to have a framework for thinking about either noise, that is the estimation error, or true variation across things. And what's going to be really nice is that as this is almost as a side benefit of doing this, is that there's a really kind of beautiful set of techniques for estimating these types of methods using what are called Monte Carlo Markov chain, Monte Carlo. I can never remember MCMC methods. I can never remember which order they go in. MCMC methods for estimating these types of distributions that are analytically kind of complicated, but computationally, there's so much raw computing power now that you can kind of do a lot with them. And that's actually going to be kind of just an artifact of these approaches, is that we're going to be able to use them to do computationally very challenging problems. And that'll be obvious in just a couple of slides. So kind of to give motivation for what we talk about, I'm going to give 3 estimation problems that are going to hopefully seem somewhat different to you, of kind of what the end goal is and what the idea is. They're going to be different types of problems in very different settings, but hopefully kind of the overarching structure that we're going to talk about today is going to make all 3 of them much more accessible as a consequence. So kind of the first example, this is kind of, if you do a random survey of a lot of econometricians, of people who work on hierarchical Bayesian models in econometrics. So Rachel Mager is one of them. It's kind of one of the most well-known ones. And one of her job market papers specifically focused on the question of microcredit. So specifically thinking about taking experiments from papers that had done basically randomized interventions expanding access to microcredit. So the idea was that there were 7 RCTs that effectively did different forms of treatments that affected outcomes related to business outcomes. So think revenues or whatever else. Half of you, one version of doing this is half of you got the treatment, half of you didn't, and we compare your outcomes. So very well-defined kind of estimates. Other ways, there were kind of other ways that this happened as well, but they were all in different settings, different time periods, not run by the same people. And you can use this to estimate tau hat, which is an unbiased estimate of the effect of microcredit in location L, which what we're trying to do is get at this true tau L, right? And so these are totally different experiments. And importantly, they had really different features and different characteristics. But, obviously as economists, we want to be able to talk about kind of generalizability as a consequence of these estimates. So we have a broad range of them. So I guess I didn't define this, but say there's capital L of them. We might want to say certain things about this, right? Like when you think about a meta-analysis, and perhaps this is a term you've heard before, this idea of I want to compare studies across different settings. I want to potentially be able to say, well, are they very similar to one another? Are they very different? Is there kind of core, do they seem to work in similar ways? Is that informative about external validity, right? So the idea being like, well, now if I did this on a different site, could I predict what the effect is? Are they very different? Is maybe the opposite version of this question, which is to say, like, is there very different aspects of these estimates? And is that driven by estimation error, or is that driven by heterogeneity? There's just like a lot of, if any one place, there's so many features, so much heterogeneity in the impact of microcredit that it's going to cause really big differences in different places. And so you're going to get just a lot of heterogeneity more generally. That's kind of a very meaningful question, right? Is to ask this question of, if we thought about this happening in a lot of places, is it noise that's causing this, or is it the fact that it's just like there's a lot of heterogeneity? And then more generally, is can we kind of improve on these predictions? So kind of famously, we're going to get to this at the end of the slides today. So Russ Chetty and Nate Hendren, Josh Angris and co-authors, and myself would have a paper thinking about how to kind of improve on estimates that are noisy more generally. We kind of combine estimates to get at better underlying estimates that are less noisy. So that's example 1. So idea here, hopefully, is just that you have a lot of treatments, you have a lot of estimates. So they don't even have to be RCTs, right? They can be any estimate. We talked about this idea of you all just go out and you measure yourself doing something, and we want to talk about underlying heterogeneity. The famous example in sports is like batting averages. The second example is a paper very near and dear to my heart by our faculty member, Nick Barbaras. This is his job market paper. It's hard to believe, but Nick's job market paper published in 2000, for those of you who know Nick. So he's not as young as he looks. And his job market paper was basically thinking about the idea of the predictability of excess stock market returns. So I know not everyone in the audience is a finance person. So just to kind of make this clear, it's like the idea is that, say, like, you take the market index, the excess return of that market index is actually somewhat predictable in the future based on historical data, like the dividend yield. And so this question is to say, well, if we think about your willingness to invest in the stock market, if it's predictable, should that affect our willingness to invest in stocks depending on our horizon? There's kind of some famous results saying your horizon on your portfolio shouldn't affect how much you're willing to invest in stocks. And the idea was to say, like, look, our returns in period T are this kind of predictable feature of lagged returns and other characteristics. So the idea was, write this down as a VAR, so a vector autoregressive system. So we have ZT, which is this RT, and XT, where XT are these other characteristics I was describing. So like the dividend yield. And so then we have this VAR, we have these parameters, alpha, capital B, which is going to be obviously a matrix. And then we have this epsilon T, which is a VAR, is going to have this, covariance matrix, sigma. And we can estimate these, we can use these to model predictions of future values of RTK. So for those of you who've ever done anything like this, this is pretty straightforward. If you haven't seen it, all we're saying is we're going to put a system of equations in, and we can use it to kind of, once we've estimated it, we can kind of predict forward what future expected values are, right? You just plug and chug into this machine and iterate forward. The idea, though, that's kind of really important here is that, riskiness in your investment is going to drive your decision on how much to invest. This is kind of finance 101, right? Riskiness is important. But the important thing is to say, like, if you take this VAR, the riskiness is not just about like, what is my level version of expected returns and the variance matrix that goes in there. It's actually the uncertainty of the parameters that matter a lot too. So intuitively, hopefully this makes sense to everyone, right? If I tell you, like, look, I predict that the return is going to be 5% in the future based off of this characteristic, you'd be like, well, how confident are you in your model? Like, how well estimated are these things? And you tell me, well, they're not statistically significant, but like has a really large like point estimate. I'd say, like, well, there's probably a lot of uncertainty in that prediction going forward in the future. And so that any prediction about what outcomes are needs to incorporate that uncertainty. Basically, the underlying idea is that when you have this type of model, not only do we have this uncertainty about the parameters, but if we want to talk about predictions going forward, we want to integrate over our uncertainty about the parameters. I know there's a lot of words there that you may not be familiar with, but does that make sense so far? Conceptually, that should be a straightforward idea, right? It's like we have this uncertainty, we want to worry about it. Great. Okay. And then example number 3 kind of harkens back to this stuff that we were talking about in the multinomial choice problem. So remember that when we were talking about demand systems for choice models, that I was going to use a different example in this, but then Judy convinced me on Twitter to use hers. So, when we were thinking about demand models, the idea was that we wanted to have flexible ways of modeling choice. So if you think about choice, remember we had that that problem about the independence of irrelevant alternatives, and we talked about, well, what can we do in that error term of our demand system to allow for kind of better substitution patterns? The idea being like, look, if I change the price on something, I should really substitute strongly into one product versus another. And the way to do that is to really allow for really flexible and highly structured ways of allowing for substitution between goods. So in this paper by Chen and co-authors, of which one of the is Chen, Chevalier, Rossi, and I'm blanking on the fourth co-author who is at Uber. But their idea is that what they wanted to do was, their underlying idea is that they want to model the labor supply decisions of Uber drivers. And so what they do is that they model the underlying reservation wage for drivers. And they do this as a function of time and individuals. And they want to allow, they don't observe this reservation wage, but they can see the decision to work and the expected wage. And they kind of use that as a way of estimating to back out what the underlying reservation wages are. But what they really want to do is they need to allow for very flexible and rich structure on the epsilon, sort of the unobserved component. They want to allow that to be very flexible in order to allow this to be to fit well. We talked about this a little bit when we were talking about the multinomial probit, this idea that we need to kind of allow for the omega matrix to be correlated in kind of arbitrary ways. But it's computationally very complicated. And so by putting some structure on the epsilons, namely by parameterizing it, kind of assuming that they're normal, and kind of embedding parametric structure and putting some hierarchical systems on it, we can actually use Bayesian techniques to kind of make this estimation much more doable, because the computational techniques in this setting are quite powerful. So those are kind of the three examples. Pick whichever is your favorite if you want to just keep one in mind. But the idea is that there's kind of three sets of types of, these are all very different examples, but all are going to kind of use Bayesian methods for thinking about this. Okay. So now what we're going to do is, you'll forgive me if this comes across as like something that you've seen before, but I'm going to give you like the version of this part of the lecture that I wish that they hadn't skipped over when I was trying to learn this when I was an undergrad. So this was like my main focus was on Bayes, hierarchical Bayes stuff. And it took me like years to figure out what was going on, because there's this kind of aspect where it's like they teach you this thing and then the yada yada something, and then you get to it. And that middle step took like a really long time to get it. It may be more obvious for you all, but I'm going to kind of walk through it very carefully just so that it's all concrete. So let's start with the likelihood. So a lot of what we've been doing so far, remember we were talking about maximum likelihood estimates. We had this idea that there was a likelihood for our parameters that given data, so we have these sets of data. Here I'm talking about kind of these pairs of outcomes, but it could be really any type of setting. This is a conditional likelihood because we're conditioning on X. Regardless, that we have some kind of IID data with model parameters and we write down our likelihood like this, right? We take the product of the individual terms. Because they're IID, we can just take the product and it gets us the joint distribution of the data. So really the idea behind the likelihood is you need to write down the full joint probability of your data set, conditional on some parameters. Here we just call it theta, right? I haven't told you what the density is. So really all the likelihood is in your back or your mind is that it's the joint probability of the data. And then if we were going to do MLE, we'd take the log and we'd maximize and we'd try and figure out what it is. But if we're Bayesian, what we'd say is, look, what we actually think of is that this parameter theta is a random variable. And then by Bayes' rule, we know we can write down the following. So Bayes' rule may not be something you have tattooed on your head, but Bayes' rule says that the probability distribution for theta, conditional on y and x, is equal to the probability distribution of y conditional on x and theta times the marginal of theta divided by the marginal of y conditional on x. So actually, I'm sorry, there should be this theta should technically be conditional on x, but you can just treat it like it's independent and then it's fine. This is a little unintuitive. I should really just write it as y comma x. Regardless, that doesn't change things deeply. So is everyone sort of familiar with, this is kind of the thing that like you should know cold, is that Bayes' rule lets you say this. And the way that I always remember it is like when you multiply by something here with the marginal, it pops it out of the conditioning sets and makes it joint. So these two together makes it the joint distribution of y comma theta conditional on x. And then you divide by the marginal, and that when you divide a joint by the marginal, that moves the variable into the conditioning set, and that's how you get theta conditional on the data. Kind of the useful and important thing, especially when we're going to talk about this stuff analytically and computationally, is that you can always just write this posterior as proportional to this product. So when we divide by this marginal distribution, this doesn't include theta. And so it's really just a normalizing scalar. It's just a normalization constant. It's not a scalar necessarily, but it's a normalization constant because it doesn't move around It just makes it so that this whole thing integrates to one. It's a well-defined probability distribution. So really all you have to worry about is the likelihood, that's this joint distribution, and the prior. Any questions on that? Okay. So basically, the three pieces you have are the posterior of theta, you have the prior on theta, and then you have the likelihood on theta as well. So what does this add to our previous conversations talking about the likelihood? Well, it adds kind of two crucial features. The first is it adds the prior. So picking a parameter that maximizes the likelihood multiplying the prior will give a different estimator than just maximizing the likelihood, except in extremely special cases. So we'll talk about that in just a second. Oh, my son is up here. Hi. Do you want? Okay. So the second thing that it's going to do is this is basically going to let us talk about the full distribution of theta, right? So when we were talking about our maximum likelihood estimate, we were talking about literally the parameter that is the maximum likelihood. And then when we talked about inference, right? So we wanted to say like, what's the confidence interval? We basically made this assumption that that estimator in the limit, we could talk about it being approximated by a normal distribution. That it's very rare that it's actually truly a normal distribution. And the normal is when it actually is. And so what you're doing is you're making these approximations. So locally, at the maximum of the likelihood that looks like a normal. Whereas when we do it this way, if we parameterize it, we know exactly what the distribution is, or at least we can generate what this thing looks like. So let's start with a simple example. So you may have seen this before. We're considering a data set of successes and failures. So each one of these is a binary outcome. You can think of that these as just coin flips, or if you want to be kind of economicsy about it, you could say these are like bankruptcy failures or something else. And we want, this is basically a Bernoulli, right? So, or a binomial where the total outcomes is n. We have a total number of failures, which is the sum of the xi. And we're just going to be assuming that this is all identical across this. Identical failure rate, p. So we know the joint distribution, right? Because what we can do here is we could just write this out. The joint distribution is inherently going to be the product of all of them. Well, each marginal one, remember, is just p to the whether or not it failed times 1 minus p to whether or not it failed. You take the product, it'll be this. We could very easily do the maximum likelihood estimate, right? So that's going to be the sum. That'll give us that p hat is equal to the sum of the x's divided by n. If that's not obvious to you, then I would recommend just take this. This is the likelihood. Take the log and take the first derivative and solve for p hat. Or solve for p, that will give you the maximum likelihood estimate. Now the question is what we already talked about. We said, look, this is our likelihood. This is our joint density of the data. What's our posterior for p look like, given the data? First, what we need is a prior, right? So for starters, just to make this easy and to kind of give you an example of something where it's trivial, let's assume it's uniform. Let's assume it's a uniform prior. So what does a uniform prior say? It says that I basically have no prior views on what the probability of p is. And so I think that it could be anywhere between 0 and 1. Then the posterior is going to be proportional to f of x conditional on p times 1, right? Because it's just a uniform. It's 1 over 1. Which is just going to give us back the same equation. Like arithmetically, it looks the same. But now the thing that we're thinking about as being a random variable is p, right? It's not x anymore. P is the random variable. We're conditioning on x. And so, this is the sort of thing where you spend a lot of time doing these, you learn that this is a beta distribution. If you get either the Gelman book, which I think I put on the syllabus. You can go in the back of the book and there's like 100 different distributions. You can start to learn what these things look like. On Wikipedia, there's also a very nice discussion of these, but this is one that commonly comes up when you're thinking about outcomes like this. This is a really convenient way of thinking about probabilities that go between 0 and 1, or values that go between 0 and 1. And we know what the parameters are because we know what the distribution is. Well, so the beta distribution is characterized by parameters. It's usually p to the alpha minus 1. So alpha then has to be the sum of the xi plus 1. And a beta term, which is this 1 minus p to the beta minus 1. So then we know that beta is equal to n minus the sum of the xi's plus 1. So what's interesting, right, is so we know what the posterior mean is. The posterior mean is alpha over alpha plus beta. That's just analytically we know that about the posterior mean. But it's worth noting the posterior mode is, sorry, there should be a parentheses here to make it clear. It's alpha minus 1 divided by alpha plus beta minus 2. So it's exactly the same as the MLE, right? So our MLE estimate, and remember the maximum likelihood estimate, is the sum of the xi over n. Well, that is literally what you'll get here if you take the posterior mode with this particular prior. So that's like a convenient thing in this case. This prior happens to give us the MLE. Does that make sense to people so far? That's not a particularly Bayesian way of dealing with this, in the sense that this uniform prior, it's important to ask the question of like, what does it mean to use a uniform prior like that? Like that's potentially a very weird thing to do, right? Like in the sense that you think it's equally likely that the probability that your failure rate is going to be 0.001 versus 0.99 or anywhere in between. You can do other types of priors. So what we can do is that we can use a conjugate prior and get sort of relatively easily interpretable posteriors. This is going to matter for what we do going forward. So conceptually, the idea is that there are these priors called conjugate priors, which you multiply a data generating a likelihood by, and that it's going to give you a posterior that is also kind of in the same family, that's analytically tractable. So, so let's assume a beta prior with an alpha, so p here for prior equal to 1 and beta p equal to 1. So the mean then, remember, posterior mean is going to be 1/2. Then, and I'm sorry, this is a typo. This should not be times 1. This will be multiplying by the prior that we just defined here. So posterior is going to then be the product of this. And what you'll get is you'll get p to the sum of the xi's plus alpha p times 1 minus p n minus the sum of the xi's plus beta p, right? So remember that those were 1 and 1. Almost looks identical, right? We have a posterior, same distribution, still a beta. That's one of the nice things about using a conjugate prior. We still know what the posterior is. And what's key here is that our parameters now are a function of this alpha p. So alpha p here is effectively the bigger alpha p and beta p are, the more that this is going to shift around what our posterior estimates are, right? So remember that these alpha and beta, those define what our posterior mode is. If alpha p and beta p were 0, then we'd get the MLE again. What happens is that if we start to make alpha large relative to beta, then what you're effectively saying is that I think that the average of P is big. And so I'm shifting the mean that way. And so what you're going to get is that you're going to get that your posterior mean is also shifted upwards, right? Because your alpha P will be large relative to your beta P. There's kind of a very cute way of interpreting this in a Bayesian setting, which is like, remember how we said like these are coin flips? Well, the way that you could think about this is that, well, what my prior is, it's like the amount of coin flips that I have in my memory of like the number of times of successes versus failures, where alpha here is defining the number of like prior successes versus failures that I've seen. And so that's going to upweight or downweight you. the key intuition here is that this multiplying by the prior shifts your posterior estimate. So like, if you think the MLE is a good estimate, and we do, right? We think it's unbiased, or we think it's asymptotically unbiased, we think it has good properties. The issue is that by having a prior, we're moving around what our estimate is, kind of irrespective of the data, right? We can put a stronger prior, we get a more, we shift our estimate more. The kind of key point though is that as we let our sample size grow, that our prior should stay fixed, and that in the limit, our posterior is going to converge to what the MLE is, our posterior mode. Any questions about that? Kind of the key point here is to just take away that, priors here are going to inherently move what your estimate is, but the hope is that they're sufficiently uninformative. So in this case, if alpha and beta are small, that it really won't affect what you're, relative to the number of observations that you have, then it won't affect your estimate very much. Okay, so we actually start with the Bernoulli first because it's useful to do that because we do sit in a lot of cases where we think about binary outcomes, right? So in that space, it's not a bad place to live. So let's consider another example where we think about normal distributions instead. So you can say we have a set of observations xi, which we assume come from a normal distribution with an unknown mean and known variance sigma squared equals 1. Knowing the variance is just here to make it so that I can do this on the slides without making the math really complicated. You can generalize this to allow for unknown variance as well. So this is intuitively the same as saying, xi is equal to some mu parameter plus a noise term, right? So it's like running a regression on a constant. And what you want to know, and so you're saying that there's some underlying constant that potentially you're interested in, and the noise is distributed mean 0, variance 1. Now we need a prior. So the only unknown parameter for us is mu, right? Because we said that sigma squared is known. So what's the prior? What's our prior over this? And by the way, actually, so just as a quick aside, one way to think about what I'm saying when I say that this is a known variance, like I know what it is you're effectively saying I have a dogmatic prior, right? I'm effectively saying I have a prior in this and it's 1, and I'm putting infinite weight on that relative to everything else. So I'm not putting it like that's kind of the intuitive way in a Bayesian framework to think about what it means to say I have a known variance. Well, I'm saying I assert that it's this value and I'm not allowing any probability mass on any other part of the support. That's what's called a dogmatic prior. So our only unknown parameter in this space is mu, like what we said. So how should we pick our priors? So I mentioned before that there's this benefit of using what are called conjugate priors. So the conjugate prior for a normal mean is also normal. And so for the purposes of this exercise, let's assume a prior with mean 0 and variance of 100. So what we do in these steps, what we'd say is, this is like before, well, we want to talk about the posterior for mu, conditional on the data. Well, that's proportional to the likelihood times the prior, which is then the product of these two normals, right? So proportional to the product of these two normals. Because remember, we know what the variance is. So you may or may not remember from your statistics class, but remember that the normal distribution has this thing in front, which is a function of the variances. But since we're not paying attention to the variances, we don't have to worry about those terms. And so all we have to do is we need to focus on the exponential terms. And so what we have is this is the likelihood term, right? So we have the product of all the xi. So this is xi minus the mean, and we don't know what this mu is, divided by 2 times sigma squared. So remember, sigma squared is going to be equal to 1. I'm just keeping it like that so that we keep track of it, times the prior, where the prior here, remember, is that we're saying that the mu is normally distributed with mean 0 and it has a variance of 100. So this is part of where like the yada yadaing happens. Basically, you want to know what this posterior value is, but you have this product of these things. Well, I told you that this is conjugate. And so actually what you can get is you can combine these terms and basically drop out any that don't involve mu. So effectively, we're going to combine them. We're going to drop out any of them that don't involve mu. We're then going to what's called complete the square. And that's going to give us what our posterior distribution is. So I'm actually going to do it on the board. I'm sorry if for some of you this is boring, but it's just, I always find it ridiculous that this doesn't get shown in person. Give me 1 second, make sure that, oh, the voice doesn't work. That's annoying. 1 second. I'm gonna use my headphones with a much longer cord in case anybody has questions. Let me see. Okay. All right. So very briefly. So how does this work? Let me turn the lights on. Okay, so we have this horrible looking expression before where what we had was we had the exponential and it was the sum, the negative sum over 2 sigma squared xi minus mu squared. And then we had times, same thing. And remember, this was just, it's basically just mu squared over 100. Well, 2 times 100. That part's not going to really matter because it's going to come out. So we have a negative. So remember that when you do the product of exponentials, now we have the sum. So really what we can do is we can do the following. We can factor out the 1/2. And so really what we're paying attention to is just this middle piece where we factored out the 1/2 and we've added these two together. And so what we have is the sum of the xi minus mu squared over 2 sigma squared plus mu squared over 2 times 100, right? Now, all we have to do is let this one go. And what we're going to get is, remember that in any individual term, it's xi mu plus mu squared, right? That's just, I'm just like multiplying it out. And we're going to be summing these up. So this turns into the sum of this. All we have to do, and I'm sorry, and then we should have divided by 2 sigma squared plus mu squared over 2 times, oh, the 2's gone. I forgot, we factored out the 2. So sigma squared and then 100. All you have to do is keep track of the things that have mu's in them. So the mu squared and the mu. And the reason for that is, remember, we care about the posterior distribution for mu. So all we have to do is figure out what are the terms that need to exist for this distribution. So we know it has to be normal. And so we know what it has to look like. It has to look something like this, where now the xi is going to be mu instead. And so we just need to figure out what is this term and this term. So the trick to the whole thing is to say, well, what we have is we have mu squared, and we have 2 of these mu squareds. We have mu squared 1 over sigma squared, and I'm sorry, we should do the sums out, right? So we should have a sum here, and then this should be n times this, because we're summing it up n times. And so what we're going to have is we'll have n over this plus 1 over 100. And this will be 2, remember, in the end. Or 1, sorry. And then this is the sigma squared term. And then for the one that has just mu, remember, we're going to have, we can ignore the 2 for right now, but the other piece of it is that there is just a mu, and then we have, so it's minus 2 mu, and we have the sum of the xi divided by sigma squared. So these are the terms that are here, and so what we know is that what we need is we need something that will cancel out this term and is basically has this piece in it. So we know that this has to be a version of what's the mu, but gets canceled by the coefficient on this. So the easiest way to think about this is that let's plug in for the 1. So now we just have 1 here. And so it has to be the case that what we're going to get is we have to get something when this is multiplied by this. When has to be that there's something, the mean has to be something such that when it's multiplied by this, it turns into this. So we know that the mean then has to be the sum of the xi divided by n plus 1 over 100. And so then, and we can kind of check this for ourselves, but that's the posterior mean. And then we know what the posterior variance has to be as well, because if we add and subtract to make it so that we can complete the square with this mean, we're going to get out this variance that I put in the slide. I'm going to pause there for a second because I know it's particularly hard to do this on Zoom doing the math. Does that make sense for everyone? Or at least is it, I think that I'm not going to walk through doing the variance component, but what you should do is basically add and subtract xi terms such that you can get, basically get it to the mean version. Does that make sense or no? I'm seeing sort of some faces. Was everyone with me up to understanding that these are the two pieces that are sticking around, right? So we had this, and then what we had was we had this additional third piece, which was the xi squared. That piece isn't going to matter. And so all we need to do is just add and subtract terms to get it so that what we finally are left with is, what we need to be left with is mu minus the sum of the xi over n plus 1 over 100 squared. We need some variance in the denominator here. And so the trick is to figure out what is the addition and subtraction that goes to cancel out in these terms. Okay. Any questions? It's been very quiet. All right. I'll keep going. So interpreting this is kind of easier than thinking about kind of the algebra that's going on. And frankly, you're not going to have to do this kind of algebra for doing this analysis anyway. I think the reason it's useful is that it makes concretely what's going on very clear. Namely, we have this posterior parameter, right? So this is our posterior mean, and we have this posterior variance. Well, remember we had a prior at 0 with a really large variance. So it wasn't a very precise estimate. It was very diffuse prior. And so conceptually, what the posterior mean is doing is it's taking, well, let's take the average. But what I'm doing is I'm taking the average, but then I'm shrinking it down slightly. I'm shrinking it towards 0 by adding this. Basically, what's happened is that I'm taking the weighted combination as a function of the variances, where I'm down weighting the sample average by my prior of 0. And so the more precise that my prior was, the more I would have down weighted this, right? Because 100 would have gone to 10 or to 1. And so then this would have increased. Or I could have shifted around the prior and that would have moved my posterior value for mu as well. And it's also would have changed my underlying variance estimate as well. The bigger that my posterior variance was, well, the more that this would have, this basically by having a large prior variance on the value, that's going to then increase my posterior variance, right? Because this is 1 over 100 to 1 over that. So the bigger it is, the more of an impact that has. Basically, there's these two pieces, right? If we make the prior more informative, it's going to shrink us more towards something. We'll also make our posterior variance smaller. Basically, as the data gets large, though, the prior should matter less. Okay, so far, we've really just been focused on single parameter estimation. What we're going to do now is we're going to consider a set of mean parameters that we're interested in across locations. And what we're going to be doing is basically creating what's called hierarchical structure on our parameters. So now we're really getting into kind of the meat and potatoes of this type of structural modeling, which is what we're going to say is let's consider means across L locations where we observe observations within each location and we model this directly. So we have, this is, coming back to our example where we're each doing this. We're going to have observations YIL in every location L. So we'll observe a bunch of observations within a location. We're going to say that that place has an underlying average, mu L, and some variance. We'll pretend like it's known for simplicity. And then the underlying mean for each location is drawn from a distribution of mu's as well. And that has some variance, eta squared. And what's nice about this is that, so a lot of times writing this in this structural way is kind of very unfamiliar for people who've done econometrics. But, the simple version of this is to say like, look, there's two pieces to YIL. There's the underlying mean mu. There's the variation that comes from heterogeneity, which is mu L minus mu. And then there's sampling variation, which comes from the variation of YI that differs from the underlying mean location variation. So it's kind of two pieces that these are both random variables that we're going to be drawing from. First, we'll draw from the MUL, then we draw the YIL from that underlying distribution. This is what's known as kind of a very simplified hierarchical multivariate normal setting. This is really simple. So why am I saying it's really simple? Well, we're saying that all the locations are independent. So you could have allowed for correlation across locations or within locations in some meaningful way. But what's nice is kind of, I said here is if you can dream it, you can estimate it. More is the idea that like, you don't have to keep things simple if you don't think that that's what fits the data. There's an element to which a lot of times in econometrics, we're trying to keep things really simple, even if it doesn't really fit the data well, in part because we're sort of hoping that asymptotically things work. We kind of pick robust standard errors and we plug in, we chug and we go. In these types of settings, actually what you want to do is kind of model the data as best you can because you're going to have to lean very hard on the parametric assumptions of what's going on. Really kind of the key details here though is that in this structure, just like with the simple normal where we have the one parameter, the estimates for all the MULs are going to be shrunk towards the overall mean. So hopefully that makes sense. You can estimate all these underlying parameters. Well, when we do shrinkage, what's going to happen is that there's going to be an underlying overall mean, mu, which these MULs will be shrunk towards, which is the population mu. This shrinkage is going to be a function of the relative variance, sigma squared, and eta squared, where eta squared is that, remember that underlying heterogeneity. Remember when we were talking about the microcredit example, that eta squared being large is a way of saying that there's a lot of variation across locations in terms of the impact of microcredit, for example. So it could be the idea that there is lots of differences in MUL across different places. And so eta squared is large. And so that's going to cause different amounts of shrinkage versus if eta squared is very small, but sigma squared is large, for example. To do a full Bayesian estimation here, basically, remember that we would have to have priors for mu and eta squared as well. And these have to be specified by the researchers. This is kind of specifying these priors is crucially what defines the idea of going full Bayesian. The idea that I need to specify priors on all my unknown parameters in order to be able to do my full posterior distribution. You know, this is the contrast. I had to make this slide because this is my dog Bays, who he's named Bays. Actually, he's here. He's asleep. Let me see if I can. He's very old now, so I got him in graduate school. Bays, Bays. Who's this? He's also blind, unfortunately. Now he's blind, so he's looking in the wall. But Bays, over here. So, you know, hierarchical Bayes in the sense that, you know, we have the underlying distribution here, and then we're getting different draws from the underlying parameters from him. Yes, Bayes. I know. I'm sorry. I shouldn't have woke you up. But actually, more seriously, the idea is that, you know, hierarchical Bayesian models are saying we're going to really talk about the full specification of the model, all the parameters. We're going to kind of specify what the prior distribution looks like. We're going to specify what the modeling distribution looks like. Basically, we have to specify some parametric distribution. And that's going to allow us to talk about the full distribution of the estimate, the parameters and the posterior of the parameters. So why would we want to add all this structure? This is a lot of structure that I'm telling you. Biz, come here. Biz, over here. And there's a lot of reasons why you might do it. So, you know, one reason that we kind of talked about some of this already. One reason you might want to put all this structure is it allows for shrinkage that's going to account for covariates. And it's going to let you think about the interaction between estimates and parameters across different locations and studies, which may be of economic interest. So we talked about external validity in the microcredit setting. So not only can we do shrinkage, but we can kind of diagnose what heterogeneity means. We can estimate posterior distribution of estimates and consider predictive distributions of the outcomes. So this is the Nick Barbera's paper that I was discussing. So, you know, we can talk about not just estimates of P of theta given X, which is the posterior, but we can also talk about estimates of the probability of X given the old X. So we want to talk about what is the probability of returns in the future, given the data that I've observed. Well, crucially, what this is doing is that, actually, this is worth seeing because if you haven't seen this before, it's a little confusing. When somebody talks about a posterior predictive distribution, what they're saying is, look, what I'd like to know is like, what's the probability of a new value given the data that I saw? Well, we know kind of what the probability, we know the posterior given the data. And so what you're going to do is, and you basically are, what you want to do is you want to integrate out so that you have the whole joint distribution. And sorry. So sorry, what you want to do is you are going to have, you can talk about this. This is basically, we could talk about a new observation. Sorry, I'm trying to see if you guys, yeah. So we can talk about a new observation given the parameter. And then what we can do is we can multiply this by the posterior distribution of the value. So we know that, right? We estimated that. And remember what this is going to do when I take the product of these is that this is going to give me f of x tilde conditional, comma, theta, conditional on the data. So it's the joint distribution of the two. And then I'm going to integrate out my uncertainty about the, basically the parameters. So the idea is that the posterior predictive distribution is saying, how do I think about predictions after having integrated out uncertainty about the parameters, accounting for the uncertainty? And so coming back to the Barbera's paper, the idea in that was to say, well, look, I might want to predict returns in the future, but I have a lot more uncertainty once I account for the fact that these things are measured with error. And so predicting new values in the future is going to be much more uncertain than they would have otherwise. And for those of you who are finance people in the audience, there's a really beautiful paper by Marty Weitzman in 2007 in the AER that talks about the equity premium, where his point there is to say, there's a lot of papers that say, why don't more people invest in the stock market given the equity premium? So for those of you who aren't macro finance, it's like the equity premium here is basically saying, well, look at how much stocks earn above bonds. And what Weitzman shows is that, well, really, if we have uncertainty about what the equity premium is, and it kind of fits this distribution, and where there's a lot of uncertainty, which like there is in the data, once you integrate out and you get this posterior predictive distribution, then anyone who's risk averse basically would massively avoid the stock market under our most reasonable parameterizations. The point is that what it does is it creates much more uncertainty by integrating over the uncertainty of the parameters, which turns basically the normal distribution of returns into something that's much more fat-tailed. Marty typically did work on climate change. So this is very in context of this, is the idea of once you have fat-tailed risks, that things become much more risky and you'd want to avoid them. The point being that posterior predictive distributions can be a really useful way of integrating and thinking about the uncertainty of estimates when you talk about new predictions. And then the last thing of why you might do this is kind of a much more, mercenary view of this is you're like, forget about this. I don't care about posterior distributions. I don't care about posterior predictives. I just have a really hard computational problem and I don't know like how to deal with it. And so they're basically, we talked about these supply and demand systems, these choice problems. There actually are really kind of beautiful ways of approaching this that are quite effective for complicated statistical models that are hard to do in non-Bayesian settings. So the paper that we mentioned, the Chen et al. Paper is a great example of this. So in all those examples that we walked through, I made these like really kind of ridiculous assumptions of like, we know the variances or things were conjugate. Like we didn't want to assume certain types of models. And I also did really simple problems, right? Well, none of that is necessary, right? So Bayes' rule is well-defined irrespective of how you parameterize things. It's conceptually, you're saying that there's a likelihood, there's f of x given theta, you multiply by the prior, that's proportional to the posterior. And so if we don't have an analytic solution, so if you don't use a conjugate or something's much more complicated, in a lot of cases, you can evaluate these different pieces, but you can't actually draw new things from it. So how do you generate a posterior distribution in these settings? So the key insight from these Monte Carlo Markov chain methods, or whichever order it is, MCMC methods, is that what you want to do is generate basically chains of estimates such that after a sufficiently large number of draws from these algorithms, that the sequence of estimates are basically draws from the posterior. So you're basically generating from this random process new draws from the posterior of theta. And the problem is that, so consider the example, the Bernoulli example. So if you didn't know the posterior parameters for the distribution, and more generally the form, how to draw things from the parametric model, the question is like, how do I create draws from theta such that they look like the posterior or basically the beta distribution? And, I've already kind of walked you guys through a painful amount of analysis today. What I want to just highlight is the kind of the main way to do this now is the thing called STAND. So I'm not going to really kind of go over the details of how these algorithms work, but it's really, the way to think about this is it's exactly the same types of problems when we were talking about MLEs and numerical methods there. So remember, we were talking about this very complicated set of methods. We have a likelihood and we need to climb and find the maximum of the likelihood. And so the idea there was what we needed to do was algorithmically find the maximum using these different methods. The challenges are similar in these parameter spaces of doing MCMC, but with more randomness associated with them. When I learned how to do all of this in 2005, the way to do this was this thing called Gibbs sampler and Metropolis Hastings algorithms. These were the kind of the default approaches. And basically, this is not the case anymore, at least amongst practitioners who use this. The way that's advocated for now is this thing called Hamiltonian Monte Carlo or hybrid Monte Carlo, which I'll be totally honest, I haven't used myself personally, but kind of everyone who's used it uses this method because it's orders of magnitudes faster than any of the default processes. It's also totally implementable using open source software. Kind of, you don't have to write your own coders to do this. Now there's this software called STAN, that's the logo on the right, where it's a statistical language that you can use in R. So basically you can call from R this thing, you set up a bunch of the parameters, it will give you kind of what the posterior estimates look like. You just have to set up what your hierarchical model looks like. So if you're going to go through this particular approach, this is the way to do it, is to do it through STAN. I think my understanding is you can also call it through other processes as well. R just happens to be one of the most popular ones. Any questions on that? I know that's a little hand wavy, but frankly, I know that this is the best way to do it. It didn't exist when I was a graduate student, effectively. Okay. So what are the downsides of going full Bayes? What's the cost of all of this? Kind of, in most cases, the biggest cost is the fact that it's parameterizing everything. In everything we've talked about, I said, look, these errors are normal, or, this is following X distribution and I have to be very specific about all the parameters that are going on. And I say we here, this is not the royal we, like me, this is like we as economists are typically uncomfortable, at least the way that the field has evolved is that in a lot of applied micro settings, we don't really want to impose that much structure on what our data generating processes are. We'd rather stay non-parametric or semi-parametric. So a good example of this is, remember we talked about linear regression. We like the idea of avoiding parameterizing our error terms, right? We didn't want to say that our errors were normal. We kind of just wanted to allow for arbitrary heteroscedasticity and do our sandwich estimators for the standard errors, right? That was kind of a key thing that we like to do in our approach. There's not an obvious analog in the Bayesian setting of something like robust standard errors. At least I'm not familiar with it. It's a sort of a semi-parametric way of doing this, and we know that it works asymptotically. There are ways to try and deal with this. So you could flexibly model the covariance structure. You could allow for a lot more kind of arbitrary covariance and try and deal with it that way. Or what you can do, and we'll talk about this next slide, is you can kind of ignore the underlying DGP. You can say, all right, I'm going to do semi-parametric methods to estimate my betas. But then when I talk about my treatment effects, I almost always, when I do inference, I'm assuming that these are normal anyway, right? That's how I do my confidence intervals. I say, take the t statistic, the relevant t statistic, and generate confidence intervals based off of that. If I'm willing to assume that those parameters are normal, I could still do hierarchical modeling using that. I'll talk about that in just a second. The other downside is that economists are really uncomfortable with this aspect of adding priors or kind of shrinking towards particular things, because how do we know what to shrink to? Doesn't this create potential bias in our estimates? And the short answer is yes, it creates finite sample bias, right? Just by definition, we talked about in these simple examples, I can pick up a prior, it will shrink towards it, that creates bias. The idea is that in the limit, when I have more and more data, the prior becomes less and less informative. But the concern is that when and I don't touch on it much today, but it's worth highlighting in the back of your minds that when you have really, really high dimensional problems, so you have many, many fixed effects, or you have many, many parameters, or many, many covariates, putting priors on those things will create bias, even if there's a lot of data. Just by virtue of the fact that these things are so high dimensional, you're going to do some amount of shrinking that your large data set didn't necessarily fix. I mean, a simple way of saying it is, if you have 10 million observations, but you're putting fixed effects for like every classroom, there's only like 20 to 30 people within a classroom, you're still going to have an impact within classrooms, even if you have, hundreds of thousands of classrooms. It's like kind of this idea of how finally are you subsetting your data when you have parameters. And so that's the thing I think a lot of folks are uncomfortable with, is this idea of the choice of priors. And so a lot of people who do work on this in order to kind of alleviate the concerns of economists will do a lot to kind of show how your results change with respect to priors. The middle ground of how you can deal with this issue is there's ways to address these issues I just raised. There are kind of middle grounds between the two results. The first one that I mentioned is that, like, let's assume that our estimates are normal. So that's how we do inference, right? We say, all right, these are asymptotically normal. Let's, do confidence intervals based off of this is the mean. I want to test whether or not it's different from 0. I do 1.96 times the standard error. So this is a result from Rubin from 1991, where he's saying, well, let's use this fact and kind of talk about a hierarchical model over that. And so what you can say is, look, I have some parameters, apologies for the typos, where we have these tau hats. These are my estimates, which are normally distributed around the true value, tau, with some standard error. And that tau is drawn from an underlying distribution, where there's some mu and some sigma squared. And what's kind of cool about this, right, is that if we had a prior on tau and on sigma squared, we could just do full Bayes here, right? We can easily talk about the posterior. We just treat these tau hats as data. This is one way of thinking about, hey, maybe we can, if we have a set of results in a literature, for example, we could talk about shrinkage estimation in that setting. All we really are exploiting here, we didn't have to talk about the distribution of the outcomes, the data generating process of the outcomes. We just focused on the fact that we're using this normality of the estimates and assuming unbiasedness, right? There's no bias term that shows up here. The only new thing that we have to do is we have to assume priors, right? We need some sort of prior to do full Bayes. And so how should we pick those priors? So the way to cheat on priors is with something called empirical Bayes. A lot of times we don't know what prior to pick, and we don't want to pick we don't want to pick something arbitrary. But what you might be willing to do is, it seems like there are kind of like natural things to shrink towards. So an empirical Bayes approach says that the traditional estimator might be good enough. So kind of the really dumb way of thinking about it is, imagine you just take your estimates and you shrink towards the overall average. Like, that seems like an extremely reasonable thing to do. Say we wanted to understand what to shrink towards if we had a bunch of observations for all of us. What should we shrink all of our underlying parameters towards? Well, we should shrink them towards our overall mean. That seems like a reasonable thing to shrink towards. It turns out if you set up the problem in a particular way, that's the MLE, right, of our overall data set. And that's what empirical Bayes would tell you to do, is shrink towards that estimator. Now, the trick is, this isn't really Bayesian in the sense that we're not talking about the full joint distribution of the parameter, because we've ignored, what we've done is we've taken this prior and then we put a dogmatic value on it because we're not allowing there to be variability in it. It's not a true distribution. We've just asserted this hyperparameter and then it's ignored any kind of variation in it. There's one terminology piece I want to describe to you all. So, because this will show up if any of you want to do Stan. So when we talk about this, you know how I said that tau is being drawn from this normal distribution with parameters tau L and this thing here, and the tau L comes from this higher level distribution. What the parameters in this higher level distribution are called is they're called hyperparameters, which sounds very cool. But conceptually, it's just any kind of, what in this is a 2-level model. So this would be the level 2 hyperparameters. You could have multiple levels, and the things that are kind of unobserved that are defining the hierarchical structure, those are called hyperparameters. They're not directly estimable. But the point is that what this empirical Bayes method does is it defines hyperparameters based off of these empirical estimates and then ignores variability in the estimates. So let me show you an example of when this shrinkage stuff can be useful, at least I think, and this is kind of it's easiest for me to do this now because I have the data. This is something from my own work. So I do a lot of kinds of shrinkage in here, but because of issues with time, I'm not going to get into it. But the simple thing is here is that this is a paper that studies the impact of Medicare on health insurance and various consumer credit outcomes. And we're using RD, but for the purposes of this, imagine I just randomly gave people health insurance around the age of 65 to some people and not to others. We're going to get into RD in a couple of weeks, but let's just assume I have the causal effect of Medicare in each location. So I have this tau L, that's like tau hat L, just like before. These are commuting zones, are my unit of, that's what L is. And there's something like 742 of them. We have a big data set. We have 5% of the United States population. So we have a really large sample, but these estimates are really noisy. So this is just the histogram of the estimates, just to give you a sense, like the actual average effect, if we just took the national sample, is pretty well estimated, and it's something like minus $30. And so you can see this is like really noisy. Like it's basically useless, to be totally honest. Like if we look at the underlying parameters, the standard errors on some of them are enormous, and for good reason, right? There's just like this one that's positive. So this is an estimate. This is the effect of Medicare on reducing debt collections. So it's a negative 30 is the estimate because it's the effect on debt collection. So minus 30, it reduces debt collections by $30. So the idea that it would increase debt collection by $1,200 seems unlikely. So what do? Well, you can shrink these estimates towards the overall mean of our estimates, weighted by how noisy the estimates are. So there's a way, if you think about the overall variation versus the standard error of our estimates, and you want to trade off based on that. Well, that's what we get with it. This is a very simple version of doing the empirical Bayes shrinkage. And you can see, I mean, I don't know if it's like stark, like look at the difference here. It's like, this is actually informative and useful. The last one is almost meaningless. All the ones kind of in the tail got massively brought in and are effectively at the mean because they're so uninformative. And so what we see is we actually get pretty large variation. We have some that are positive, but these are all pretty, still pretty noisy. And we see this big variation. And what's cool, and this is a pretty classic way of presenting this, is you can see the unshrunk estimates relative to the shrunk estimates. So the way that these estimators work is that there's a kind of a weighted trade-off between how noisy they are and the overall variation. And so what's happening is for these unshrunk estimates that are really big, they got shrunk right into the mean. That's why they're kind of at this level value. And there's this trade-off here on both sides. So you can see kind of the shrink. This is the unshrunk estimates on the x-axis, and these are the shrunk estimates on the y-axis. And this has a substantial impact. Oh, it kind of got cut off here. I got to fix this. This makes our estimates kind of a lot more useful and informative. We do this. We actually do another step on top of this, which is what we say is, can we shrink them not just towards the overall mean, but can we shrink them towards kind of like a best predicted value, which is a function of local characteristics. And so we do that, and then we kind of get even more informativeness from this. You know, this trade-off, though, the shrinkage trade-off is that what it's doing is it's improving mean squared error effectively. Excuse me. That's why we were doing shrinkage historically, right? Is that we were basically getting improvements on the mean squared error by increasing bias, slight increases in bias in order to massively reduce the noise. So that has trade-offs, right? In the sense that we worry a lot about unbiasedness in economics. We want unbiased estimates. That's kind of like the catch-all. That's why we want causality. And so it's very important if you're thinking about shrinkage to think about, okay, well, what problems is this going to create if I am shrinking in some way? Am I shrinking towards something that's meaningful? Am I biasing? Am I reporting this in a sort of a clear way? If it's something that's so noisy that it's not informative, a small amount of bias can be very useful, just because it will make it so that it's much less uninformative. I think, frankly, I think an estimate that's $1,400 but has the standard errors of 3,000 are basically useless because the confidence interval covers such a large range. If we're trying to do prediction, especially forecast error is much more important. So this is mean squared error is much more important than unbiasedness. And so if you're somebody working in finance or asset pricing, this can come up as well. Let me kind of just to wrap up, having this structure that we just talked about kind of gives intuition for a lot of other settings as well. And Scott, I wanted to kind of harken back to when we were talking about lasso a little bit, because I kind of posed lasso as this minimization problem, kind of straightforward, it's model selection, et cetera. What's cool is that lasso can be viewed as a form of having a Laplace prior on the betas in our regression methods. So, and whereas other regularization methods like ridge regression just use a different type of prior, or like a less sharp peaked prior. So ridge regression uses a Gaussian prior. So you can kind of see here, this purple line is the Laplacian prior, and you can see it has this very kinked point at 0, which is part of the reason why it has such a big impact on shifting things to 0. It actually puts like positive mass in a non-smooth way at 0, which causes things to bang up against 0 if the prior is sufficiently dogmatic. And so what's cool is you can think about, this penalization term in this minimization problem is actually just putting a different type of prior on our betas when we do regression. So this is kind of a really interesting way of thinking about, the reasons behind Bayesian methods also motivate regularization and vice versa. So if you can keep both of these in your mind at the same time, that can be very valuable. The idea that, well, what we're doing when we do lasso is we're putting a certain type of prior. And so maybe there are other methods that kind of do combinations or more complicated things. This is especially going to come up when you think about very high dimensional models, because the priors that you put could potentially be very dogmatic in these spaces. Let me wrap up. Let me kind of conclude here. So, my view on this is that adding this structure, this is kind of a very concrete place that even for pretty reduced form applied folks, that you have to add a lot of structure, but it can really be very powerful. Like we talked about, it gives you the posterior distribution, and you can talk about kind of predictive elements of it that are very useful. I will say that computationally, this used to be a huge bear. Like this was the kind of thing where you had to spend all your time thinking about it. And my sense is now that if you want to try and do this in kind of simple settings, that this is pretty straightforward. If there are people in the audience who feel differently, you guys should speak up. But my sense is Stan has made this a lot easier to at least try and do. I think they're widely applicable in a lot of settings. So finance and IO are kind of two of the examples, but in labor and public, empirical Bayes methods are coming up more and more. And I think, empirical Bayes, as hopefully one thing I didn't mention here, but the empirical Bayes, part of the reason it's so valuable is that you don't have to do any of this posterior estimation thing. You can just say, I have my estimates and then I shrink them towards something else. I don't need the posterior distribution per se. It's not quite as much work, as I guess what I'm saying. Basically, it's useful to kind of think about how shrinkage can be incorporated in different methods and how it can be valuable. Kind of, the decision tree of deciding how to use these methods isn't obvious, but for me, it kind of falls into 3 types of categories. So I have a lot of noisy estimates because maybe I ran a lot of experiments or I have a lot of heterogeneity. I want to look at the distribution of them. And I want to kind of exploit the fact that they can be shrunk in some way. So I want to use that joint information to improve that. So that was like my example in my paper. I have a complicated statistical problem that I need to generate an underlying distribution from. So that was like that IO example, thinking about demand estimation. I think that can be really valuable. And then finally, when you want to think about predictive outcomes and think about uncertainty and incorporating parameter uncertainty, that can be really valuable as well. And I think it can be useful to think about Bayesian methods in those settings. So I put some example papers at the end here if you want to kind of look at some other papers that do this, but I'm out of time, so I'm going to stop.